Okay. So Luis, you are the only one that is outside, so but I can hear you, okay? But the rest cannot, or maybe yes, I don't know. But Barbara does not.
Okay, no problem.
So the thing is, my idea is to like perform the whole cycle of creating a constitutive law from the very beginning, and then try to run a case and see what happens. No? I think in your case, you are all of you in the master branch, no? And if you don't follow me, I wait for you, okay? You can open the Git Kraken and check that we are in the master branch. You let me know and we move forward.
From my side, you can move on. I'm gonna have a look on what you are doing, and afterward,
Okay.
I will try to reply it.
The thing is, we're going to create a new branch from the master branch because we can create a branch from a branch and so on, but it's not really the point. You are in the master? Okay. Usually, are you in the master?
Yes, I have a master.
Okay. Wait a minute. And we are going to create a branch from the master to create our constitutive law, and then we remove it because we're not going to use it. But, just to practice. Perfect. Like hacking in movies. So we're going to create a branch with this button here, and then we are going to we'll write some name. I don't know. Adding constitutive law. As you can see, the style guide of the branch names is with this symbol. Okay. And now we have created a new branch. Okay. Up to now, it's a local branch. I mean, it's only in our PC. It's not in the GitHub cloud. If we want the branch to be in the cloud, we have to push. I think, well, we can do it, no? But if we do it, it's going to appear in the GitHub repository when it does it. And we're going to check. I'm going to the repository. Now it has pushed the branch. And if we go to branches, here we have the branch. Ah, no. No, yeah, exactly. It's this one, no? Your branches. Okay. So we have created the branch. So now we can start doing whatever we want. Are we synchronized? Sorry. You have created the branch?
I have created the branch, but I haven't pushed it.
Okay, it's not necessary. It's just to demonstrate how it's done. And the thing is, I think that we can do like a global overview of Kratos in general, okay, from the top to the bottom, quite fast, but in any case, it's necessary. As you know, the top level file, I'm using the Visual Studio Code, by the way, and with Control P, you have this capability in which you can write analysis stage, and it will redirect you to it. If you press enter, you go directly. Okay. This is for me, top one macros of Visual Studio Code. Okay. If you're not in the analysis stage, please tell me or let me know. ¿Estáis en análisis? Vale.
No, I'm running Visual Studio Code.
Okay. And you, Luis?
Yes.
Okay.
Faster.
So this analysis stage file is like the top one, which is the one that performs the time advancing loop. Okay, as you can see, whenever you run the main Kratos.py in the case folder, you're running this run method. Okay. So it initializes everything. I mean, it reads the geometry, creates the constitutive laws, the properties, it does everything. Then this run selection loop is the time advancing loop. No? And as you can see, it does the predict, which in dynamic calculations, you have to predict the velocity and acceleration and then correct it. In static, does nothing, I think. The solve solution step is the Newton-Raphson loop. Okay. This does nothing. I mean, as we will see, a lot of times I'm going to say this does nothing, but because the implementation is really general for any case, for fluid, for solid, for whatever. So in our solid case, it may be that it's not really necessary. This initialize solution step and finalize solution step are methods that are called at the beginning of the step, not during the iterative process, only once at the beginning and only once at the end. Okay. And output solution step is like when called when printing the post processes. No? And then for more details in the initialize, we can see everything here. No? But as an overview, this is what it does. And here we can see that the analysis stage has a get solver method. Okay. This get solver, it's a Python interface and structural mechanics, static solver, for example, no? Which is the one that you are using for static calculations. But as we can see here, it does almost nothing, but because it is a derived class from the mechanical solver. If we go to the mechanical solver, which is structural mechanics solver, Control P, structural mechanics solver. And here we see that this is the main class, no? Which has the default parameters that we have seen a lot of times, no? Usual stiffness that are read from the project parameters JSON. The tolerances, everything. So this is the Python solver, which is inside the analysis stage. Okay. And this solver is the one that does more or less everything. And here in the end, here you can see that our length strategy, line search strategy, Newton-Raphson strategy. So this solver, this Python class object, which is called solver, has inside, I mean, this is a mess, okay? But since we have it in video, we can see it and you can ask me afterwards. But this Python solver has inside a C++ strategy, okay? Which is created in here, Newton-Raphson strategy, or line search strategy, or arc length strategy. No? In our case, in your case especially, is the Newton-Raphson strategy is the one that you're using. And it's this one. In Python, whenever you see Kratos multiphysics that something, it means that 90% of the cases, it's a C++ implementation, but it is translated to Python, okay? So if we go to this residual-based Newton-Raphson strategy, it's here. .h, as you can see, is a C++ file, a header, and it's this one. Let me go up. So we are entering into C++. Okay. Are you all in the residual based strategy? What is the residual based strategy? Okay. It's not necessary you to have the
Yes,
speakers.
I don't have this one. Speaker. What do you mean?
No, it's not necessary you to have them. I mean, you won't listen to Luis, but
Okay.
I mean, because maybe for you it's a mess to hear me twice. Okay, so and this is the C++ strategy, and this is the one. I mean, analysis stage rules the time bunching scheme. The Python solver does almost nothing, only has this strategy inside, and the strategy, what it does is the iterative correction of the displacement until it is the solution is converged. No, so it does a lot of work, and inside has several stuff. No, this is different ways of constructing the Newton Raphson, but I'm going to solve solution step. The solve solution step is the method that we have seen before in the analysis stage. This one is exactly this one, okay? But translated to C++. And as a style guide, wherever you see a variable which is called m something, it means that it is a member variable of the class, okay? So it's something that is from the class, a member variable or member, yeah, something, that is only inside the class. And in this case, this A is the stiffness matrix. Okay, so it's a matrix we have seen here. We can see here. Dx is the displacement increment, okay, or the correction. And B is the right-hand side, or it is like the internal forces minus external forces. No, so the equilibrium measure, which is the residual, let's say, the force residual. No, and in here it sets everything to 0, etc. Here we can see that there are several objects here, no, like the scheme, no. The model part, you have seen that it is like the geometry container. It has the nodes, the elements, the conditions, and the submodel parts. The scheme is a class that do several stuff related to, especially to in dynamic calculations, is like the Newmark scheme, okay, or the Bossack scheme. It updates the velocities and these issues. We can see an example here. Still based Newmark scheme. Here you can see an example of a scheme. But you haven't used this one, okay? But in any case, no, but this does nothing. If we go to a scheme, which is the base one, has methods like calculate system contributions, which performs a loop over the elements. No, in this case, it calls an element, it computes the stiffness matrix of the element, and then another object builds this into the global matrix. But I think I'm getting into too much details. Okay, so the scheme. The convergence criteria is necessary, no, to see if we have converged or not. You can see an example eventually. Convergence criteria, no, it's the residual criteria. And in this case, you can see more or less what it does. Computing the forces the norm of the forces and of the residual. There is also a displacement criteria. I mean, you have all of them in here, convergence criteria, no? Something that informs to the strategy whether it has converged or not. This one. And as we can see, it is a member variable of the strategy. And then we have the builder and solver. Let me find it here, builder and solver. And this builder and solver is a very important class. This one, for example, residual-based elimination builder and solver. We have several builders and solvers. No? What the builder does is perform a loop over the elements. The scheme will compute the contributions of each element to the right-hand side, to the left-hand side, and then the builder will have the global structural matrix, the huge one, no, and will add the contributions of each element to the global one, which is the build function. I mean, there is a method which is called build. This one is huge, one of the most important in Kratos. As you can see, the input are the model part because it has all the elements, all the conditions, all the nodes. The stiffness matrix, the global one, I mean the huge. The right-hand side, I mean the residual vector, the huge one, system vector. And in this case, here we have the array of the number of elements, the number of conditions. And we perform in parallel a loop over the, in this case, over the elements. The first loop is over the elements. The scheme for each element computes the element contribution to the left-hand side and to the right-hand side. And then we assemble it. Assembling is to the global matrix, we add each of the contributions of each element. Then the same with the conditions, because the elements can contribute to the stiffness matrix, obviously, no? By adding this B, C, B, whatever. It can add some internal forces because of the massive forces, because of gravity. But the external forces, the element does not know anything. So this is why we call to the conditions, because the conditions are the point load, the line load, and pressure load, no? And this load, they work as elements because they have geometry. They are lines, they are triangles, they are something. And they add their contribution to the right-hand side, to the external force, no? You are adding some. So this is why we need a loop over the elements and the conditions. And they work really similar, in a similar way. And in this case, we built everything, no? Because we have now the global matrix of stiffness and the global right-hand side, and in which all the terms have been added. Nice. This is the builder and solver. As you can see, is one of the most important. And also, after the building process, the builder and solver also solves the system. It has the stiffness matrix, it has the residual, so he can compute the displacement increment. No? This is build and solve. So it builds A, stiffness, it builds right-hand side, B, and it computes the X. As you can see, there are some cases in which you don't want to compute the stiffness, you only compute the residual, whatever. Once we have computed the displacement increment, we have this update database, okay? This update database, what it does is the displacement of nodes are updated. So according to the dx, no? And the position of the nodes is updated also. So you know the displacement increment, so now the position of this node is going to be in here. Then we have this finalized nonlinear iteration. So we will see afterwards that the constitutive law, you can do some operations before the step, before the iterations, after the iterations, after the step. We have all these options. We are not going to use all of them, but we have the possibility just in case. And now we check if we have converged or not with this first correction of the displacement. No? In elastic conditions, we end here because the displacement, the increment of displacement is going to be exactly the one needed. So we finish here. But if not, here I mean, okay. But if not, we're going to enter into the while loop until we reach convergence. Okay, so the Newton-Raphson, the classical Newton-Raphson, no? And during this loop, we're going to repeat the same process. Initialize only iteration. We're going to do whatever we need before the iteration. We're going to do the build and solve again. No? We're going to update the database because we have to update the displacement, the position of the nodes and everything. Finalize only iteration, which in our case is going to be nothing. And then we check convergence again and again and again until we converge or not. And this is the very same message that you see when you don't converge in the stream. You know? So you have seen it sometimes. And then we compute reactions at the very end. So this is the global behavior of the strategy, which, as you can see, it does more or less everything. No, it rules the world. So this is for the strategy. The builder and solver, we have seen it. The scheme is really simple in static conditions. Okay, in static cases. So which is the element that you usually use? You are using the small displacement. Yep. As you can see, the element technology is in the structural mechanics application. Okay. And we have more elements, but you are not really interested up to now. Okay. So I think all of you are using the small displacement element. And in this case, the most important method is the calculate all. Okay, so the scheme or the builder and solver calls this method. Okay, when building the system matrix, calculate all is okay. I want you to compute the stiffness matrix and the right hand side. And you can see this calculate stiffness matrix flag, which is a Boolean, so it's going to be true or false. This is because for optimization purposes, because sometimes you want only to compute the stiffness matrix. Sometimes you want only the residual. Sometimes you want both. So we separate the cases. I mentioned this because afterwards in the constitutive law is going to happen the same. So in here, the stiffness matrix is resized to the required dimension, okay, because the element is general. And this mat size, it depends on the number of nodes, obviously. So it resizes everything. The same with the right-hand side, the residual. This method, calculate kinematic variables, is like computing the shape functions, okay, which is n, the derivative of the shape functions, which is this. Matrix B is it's called the formation matrix Everything is in the Eugenio's book. I mean, it's not necessary to know it now. In this calculate constitutive variables, you can see here as if you remember, the constitutive laws has this R values container, no, in which you have seen that it has the stress vector, the strain vector, the constitutive matrix, whatever. These R values are created here. The element creates it, okay, and the element adds whatever he knows. For example, the strain, because the constitutive law does not know how to compute the strain because it doesn't have the information. The element is the one that computes the strain because he knows the position of the nodes, no? So the element computes the strain. And the strain is added to the R values in here. In the set, oh, mierda. Bueno. The set constitutive variables, it adds all this stuff. I'm the one, no. Calculate all here. Ah, no, because I changed. Okay. And now we have created the R values and we have included the strain vector. Then we call the constitutive law and we call calculate material response, which is the one that you have seen. I think that you have been reading the calculate material response Cauchy, no? And this is the very same line, okay? Inside it checks which is the stress measure that you want, but by default is the Cauchy, okay? So in here, we are going to call, the element calls to the constitutive law to the calculate material response. So it computes the stress and it computes the constitutive matrix, the tangent constitutive tensor, no? In here. So in here, the law computes stress and the tangent constitutive tensor. And then the element, once he knows the stress and the tangent constitutive tensor, he can compute the stiffness matrix, which is B transposed C tangent B, no? At each integration point and adds them. And the residual vector, which is B times sigma, B transpuesto por sigma. And it does this for each integration point, adding the right-hand side and left-hand side the element at once. And then the builder and solver will take this and assemble everything. Okay? So this is what the element does. And now we're going to move to the constitutive level, which is our main interest, no? So let's go to the. By the way, as you may have noticed, we have two main applications. No? The structural mechanics application, the one that has the elements that we have seen, as the constitutive laws, no? In which we have 90% of the constitutive laws. The thing is, the simplest constitutive laws, like the linear elastic, plane strain, plane stress, are in the structural mechanics application because we decided that these constitutive laws could be used by a huge amount of people. No? But if we want to use plasticity, damage, these more difficult constitutive laws are all in the more advanced application, the constitutive laws application. No? But let's going to start with the simplest one. This is because I'm going to the structural because only the simplest one are there, also constitutive. And for example, the elastic isotropic. Okay. I'm going to close this. The elastic isotropic. In here. And as you can see, we usually have the CPP file and the H file. Okay, this is really common in C++. The H file is the so-called header file. Okay, and the CPP is the implementation file. This is done that way, I think, for two reasons. One is optimization. Okay, because in this way, if you modify the CPP, it only recompiles the CPP. But if you implement everything in the H, all the files that are related to this class are going to be recompiled too. Okay, so it makes a difference to do it that way. Another thing is for style or reading easiness I mean, it's really easier to read if it's separate. In the H, we define the class, which is the parent class. We'll speak about this in the following. Also, we define or we declare the methods. Okay? For example, we have a method which is called getLowFeatures, workspace dimension, calculate material response PK1, but we do not implement anything. They are only declared. So in a fast way, you can see which are the methods that are implemented in this class. And also, at the end, we all implement those that, like this one that is one line, it doesn't make a difference. Okay, but if the method is really long to implement, it is in the CPP. And also, in the end, we should have the member variables. In this case, it doesn't have any because it is elastic. But for example, in plasticity, in the H, at the end, we have the member variables or historical variables. Okay, like the dissipation or the threshold plasticity. These are always declared in the H. And in the CPP, we implement everything. Okay, the details of the implementation, what's being done there, it's everything in the CPP. In this case, in the isotropic 3D law, in the calculate material response, no, which is the one that's more important, what does it do? I don't want to go into too many details. No, in here, as you can see, there is this flag of compute stress, compute constitutive tensor. This is what I was mentioning before of the element, no? Because sometimes you only want to compute the stiffness matrix or the residual. And this is translated into computing the stress or computing the constitutive matrix or computing both. So we always differentiate in the constitutive level, what do you want to compute? No? Also, as you have seen, Ali, it really makes a difference to compute or not the constitutive tangent always. Okay. And so if we want to compute the stress, it's a flag. In here recovers the stress. If it puts the ampersand, it means that it takes the stress as a reference. So if you modify this R stress, you're going to modify this directly. They are just like twins now. They are related because of the ampersand. This means that we are taking this entity as a reference. This is why we add this R. So it means be careful because if you modify this, you are going to modify those. And here we have this method, calculate pK2 stress. Let's see what that is to. As we can see, this from the strain multiplying by some constants. Essentially, what it does is to do C times epsilon. Okay, classical constitutive law. C times epsilon. And if you want to compute the constitutive tensor, you compute the elastic matrix, which is like this. It's a 6x6 in 3D, which depends on the Young modulus, on the Poisson, whatever. Eugenio's book, classical. And then we're finished because we have stress and we have the tangent constitutive tensor, which in elasticity is the elastic one. No? So we have finished. And this is what we are going to try to reproduce. Okay, now. But let me introduce the rest of the methods. As you can see in elasticity, all the stress measures are equivalent. Okay, small strains, small displacement. So all of them, the PK1, the Kirchhoff, Cauchy, they are all calling to the same method. They calculate material response PK2, but it is always this method that can be confusing. The element knows if he's working with strain or not. In small displacement, the element works with strain. But in large displacement, the elements, they do not work with the strain. They work with the formation gradient matrix. So if the element does not feel the strain in the R values, the constitutive law doesn't know how to proceed, no? Because I don't have any strain. What do I do? And in those cases, we compute an equivalent strain according to the F, to this matrix. Okay, but it's just in a weird case that you are using a large displacement element with small displacement constitutive law, which is really weird. Okay, but we want to always Kratos work. Okay. And that's it. Okay, I mean, this calculate material response in plasticity can be huge, no? Because you need to check the yield stress, you have to compute plasticity, whatever. I mean, it can be huge, but in elasticity, it's really simple, as you can see. Everything is so good. It's good. I mean, it's clear, Luis.
Yeah, so far so good.
Okay.
I mean, a lot of information, but anyway.
Yeah, but it's gonna be recorded, so
we can go back and see it again as many times as we need.
Exactly. The initial material response, I think, is the equivalent to the initialized solution step. Okay. If you need to set something at the beginning of each time step, you can do it here. In this case, it does nothing. As you can see, it does nothing. The same with all the measures. Finalize. Do you need to do something at the end of the step at constitutive level? We do nothing. In general, I don't use them, but who knows? These calculate values method are used for printing purposes for Git. Okay, when you want to print something, imagine that you want to print the Cauchy stress vector. Obviously, we don't want to store the Cauchy stress vector in memory because it is expensive. So we recompute it, and then we print it. And this is why the calculate value is used. You need the von Mises stress? Okay, we recompute it and we print it. It is different when we really have storage of this variable, no? Like could be damage or plastic strain. In those cases, we are not using the calculate value, we are using the get value. Here maybe it's not here because the elastic does not storage anything. And in damage, for example, in damage, since we have storage the damage or the threshold or whatever, we print or we are able to get the value of this by means of this get value method. Okay, so this is the difference. If you have storage this variable, you are going to call the get value because you don't need to calculate it. You are only getting it. But if it's something that you don't have it in memory, like the Cauchy, the strain, the constitutive matrix, whatever, and you have to recompute it, you call to the calculate value. This is the difference. And the hash is the one that informs you whether you have this you have stored that variable or not. For the damage, it's going to be true because you have it in memory. But for the Cauchy, it's going to be false. This is the way that the element can know if the constitutive law has stored this or not. And let's go back to here. And this is more or less like the summary, no? So we can create our constitutive or our new constitutive law. What I usually do, I think, okay, this is my catalog of constitutive laws. No, I have 3D elasticity, 2D plane strain, I have damage, I have whatever. Which is the kind of constitutive law that I want to do in my case? For now, imagine that we want to do a modification of the elasticity 3D. Okay, we are not going to modify anything, but imagine, no? So in Kratos, it is object-oriented. So in general, you create your class as a son or as a child of another class. So you inherit all the methods and member variables of the parent class. No? If you want to modify a plasticity law and adding some detail, it is optimal to, okay, I want to be a child of the general plasticity, so I inherit all the methods that the parent class has and all the member variables, the plastic strain, whatever, and I only add those that are required for my new child class. No? So in general, what I do is to derive my new class from the Elastic 3D law, because it has some basic stuff, no, like computing the elastic matrix. I don't have to re-implement this. It is already in the parent class. Or computing this green Lagrange strain, it is already there. So I reuse it. And it's really useful because if 2 years later, they discover a mistake or a bug in the base class, if they solve it in the base class, it is automatically solved in your class because you are not re-implementing anything. It's in the base class. This is the usefulness of it. Also, not to re-implement the stuff again or copy-paste. You know? So in this case, imagine that we want to create another 3D elastic law. So it makes sense for us to derive this class from the elastic 3D law. Okay. So what I do is to, okay, I'm gonna search for a constitutive law of which the parent class is the elastic 3D law, because I want to do the same. In this case, the linear plane strain, it is like that, because in here, linear plane strain, it defines the linear plane strain class. Public means my parent is elastic isotropic 3D. So this linear plane strain is a child of the linear elastic 3D law. So this is the case of our interest. No? So I'm going to, I have it here. In here we can see structural mechanics, constitutive folder. Constitutive law, application, constitutive folder. Okay. In general, we are going to implement our constitutive laws in the constitutive laws application. No? But this linear plane strain, as it is really basic, is in the structural. But in any case, the linear plane strain, I'm going to copy it. I mean, if you want, don't do it now. I mean, do it whatever you want, because I don't want you to get distracted and stressed. And so we copy this into the constitutive laws. So we have it here. Okay. As you can see in the Git Kraken, hey, you have added something. So we can get track of the changes. Okay. Let's change the name. Trial CL. Where is the other one? This one. Trial CL. Okay. Now we have the CPP and the .h of this copied constitutive law. No, no Ricardo, whatever. No, it is not necessary. It's a comment. First thing, the H. I always start with the H file. Okay. In here, Kratos linear brain strain law. This is not the name of our law anymore, so we have to change it. We have to decide the name of the. We're not in the structural mechanics application. We are in the constitutive laws application. Constitutive. I think it's fine. Let me check. Constitutive laws. That's okay. We're gonna trial CL, new name, and it is a son of the elastic isotropic 3D. This is correct. But in here, this linear plane strain is no longer like that, no longer like that, no longer like that. No, no, no. This is fine. This is fine. And now there is a decision. We have to declare again the names of the methods of the parent class only if we want to modify them. If not, it's not required. So in this case, since the elastic matrix is going to be the same, I don't want to re-implement this. So I comment it or I erase it or whatever. In fact, I'm not going to use any of it because we want to do it from scratch, no? The same with this. This is not necessary. No. Okay. Okay. And now we have changed the name of the formal copied class to our new name. This is correct because we need to include this isotropic because it is a parent, no? Because otherwise he doesn't know what is this elastic isotropic.
Alejandro,
Yeah.
there you are calling the parent class, right? When you set this include custom elastic.
Yeah, this include is like load this file, which is exactly this one, in which
So
we declare the parent class.
with
the elastic
all of the
isotropic
methods
class.
that are in there.
Exactly, all the methods,
With
and all the member variables, everything.
And we can, for instance, include more than one if our constitutive law is a mixture, for instance, of 2 or 3 of them, right? Or
yeah, it's not really advisable to do a derived class from two classes. It's not really common, but I think it could be done. But you have to include all the files that are required in terms of information. Yeah.
okay, thank you.
And in this case, I have to modify this Kratos trial CL. Kratos trial CL. Okay. In here, if we do a good job, we should fill all this with details. No, this constitutive law does whatever, or I've based implementation in whatever paper, this kind of stuff. And this is not necessary because we are repeating. This is defined in the base class. Okay. So we have changed the name. We don't want to modify any of it. I want exactly a copy of the parent class. Okay. Let me remove this. So I want it empty. Now it's empty. Let's go to the CPP. All these linear plane strain have to be removed or modified with the trial CL. I'm going to find and replace. Should be fine. Now it's fine. I'm going to remove everything because I want it empty. Now, and in here, as you can see, it is including the linear plane, so the copied one. We need to put here the trial cl.h and the constitutive laws application variables. Because we have changed also the application. Okay. So now we have created a constitutive law, which is a derived class from the elastic isotropic, as we can see, and does nothing. I mean, everything is implemented in the parent class. So in general terms, it is exactly like the parent class. So because we haven't modified anything, everything is inherited. Okay. So now we have to register this constitutive law. Now that I've created this, I'm going to do a commit, including here.
Alejandro.
Yeah.
Just a quick question.
You have muted yourself.
Just a quick question. Sorry.
Mm-hmm.
In this case, you are retrieving all the methods that are in the isotropic
in the parent class. Yeah, I'm retrieving all
class.
the methods. All the methods, all the type definitions, all the member variables, everything.
Even so, you need to define this .h file. I mean the region file, because
which one?
It does basically nothing. I mean, if I understood right, because the trial .h file.
It does nothing up to now because I mean it really makes no sense to create a class that does everything like the parent, no? But now in a minute we're going to add something, no?
Okay, great.
This is why, because otherwise you could use the elastic and you're fine.
But in the case you just make changes in the CPP file, we have to create this .h file.
I mean, you could do everything.
My point.
Yeah. You have to do it because you have to define the class anyway. So I mean, only CPP does not work. It has to be only H can work, but only CPP does not.
Okay.
You could do everything in H, but you have these performance drawbacks. Okay, so it's usually better to separate.
It's clear for me. Thank you.
Okay. So let's register the constitutive law, no? Because now we have the class, we have the files, but if you put the name of the material JSON, it does not, it won't recognize it. Kratos doesn't know which is the trial constitutive law, so we have to register it. And how to do it? It's I think it's here. In this constitutive law application, CPP, which is like the IKEA catalog of the application. You have registered everything, no? You can see here all the, this is the register name of the constitutive law. So we have to add ours. Trial CL. I'm gonna put this name here. So now it's registered once. We have to do it in several places. I think this is already okay. Let me check it. Yeah. Constitutive law application CPP. Constitutive law application.h, in which we include the file slate 2 times. And I think in this file also I have to add this.
Okay.
I think it's like this.
No estás compartiendo pantalla. No estás compartiendo pantalla.
Fine. Fine. And then this stuff.
Sí.
Oh. No. It's out or not. Because I did it twice, I think. No, it's not necessary to do it twice. It's fine. I'm slow because I want to check everything. So, yeah. So in the CPP, in the H and in the custom Python, add constitutive laws to Python. So in here, again, trial SQL and a block like this. Register. Okay. I mean, I know that it's a pain in the ass, okay, but it is what it is. So now, obviously, it's not going to compile at the first attempt because I suppose that I've made a lot of mistakes. But now Kratos should detect the new file, should compile it, and register it. Now everything is going to be read.
Meanwhile, it's compiling, Alejandro. One very important question.
Yeah.
How can I debug, for instance, the CPP file to verify if there is a mistake over there in the coding and stuff like that? It's very important.
I mean, like running a case.
Sorry, running the case.
You mean? Yeah. Yeah, we can do that in another session, but it's mainly using the Visual Studio, not the code, the Visual Studio that you install it at the beginning of the installation. We can use the Visual Studio to debug.
Okay, great. Because
so we can put the checkpoints and
okay, thank you.
And also, this is if you want to really go into details. To print some stuff, we will do it in this session, and we can print on screen. Okay, I want to see the stress vector or the strain or whatever. We will do it. And it's compiling the constitutive law. Now it's compiling the files that were modified to the new registration. Up to now, it's going fine, surprisingly. Oh, first attempt. This never happens, okay? But it's going to be recorded. Okay.
That's the point. It's game time, huh? Training is training, gaming is gaming.
So now we have the constitutive law empty. So it's going to be the same as the elastic case. What we can do is to create a simple case. Let's do it. just to run the example, no? See what happens.
Sí, yo hice el mismo análisis y por eso aquí hice con más tiempo. Yo acabo de correr la simulación con más tiempo.
It should be
Esa máquina.
going to go. Yeah, 4 elements or something. No, or 1, no? Maybe one. One quadrilateral, and that's it. Ah, no, it has to be 3D. Shit. Has to be 3D. Okay. Has to be 3D. Because our constitutive law is a derived class of a 3D constitutive law.
Bueno, por ahí bien ahorita, sí, porque digamos en este paper que tú tienes abierto no muestran la gráfica de paper que tú encontraste en el otro paper, no hay una comparación computacional y la curva experimental y es muy similar, solamente no estamos usando la curva experimental.
I'm gonna fix, I don't know.
Sí, en eso nos comparan las dos curvas.
And a load. Pero wait.
Sí, aquí no lo comparan en loads versus display, creo que es la que te muestra, pero muestran los dos casos.
No, I want next here. Have to save. LCL by calculation. Okay, so let's run it with the elastic parent one to see that everything is fine. Okay, that's good.
Sí, pero entonces si tú ves esa curva, te muestra las dos comparaciones computacional.
I'm going to put the echo level in 1
Dos puntos
to see the iterations.
y el otro es el elementos no lineal. Entonces te muestra que son similares. En el otro paper, normalmente están los dos experimentos. Podría ser que una prueba no fue bien fabricada.
And this is the one with the elastic law. So now if we put in here LCL, he should find it. It worked. I don't know if it writes the constitutive law, maybe not. But in any case, it's gonna be the same result because it does exactly the same. Now, let's add something to this law, no? For example, let's modify the main method, the calculate mathematical response. This one. It's gonna copy it. Here, obviously, now we are not doing the elastic isotropic. Okay. And we have to add it to the age, because in here, this implementation, we have to add this method to the age. Copy to the age. This override means that you know that this method is also defined in the parent class. You know it. This override, it's like if you put override and this method does not belong to the parent class, you'll have a compilation error. So it's a way to ensuring that you are modifying exactly the same method. Because it happened to me in the past, for example, that you put calculate material response pK2, but you made some typo mistake and you put pK3, and it compiles because you are adding a method to the class, but you are not modifying the method that you want. You are creating a new one. So if you put the override and you make the mistake, the compiler is going to say, hey, you have put here override, but it is not overriding the method. It's a way to be sure that you're modifying.
No perder ese material.
So now, okay, if we compile like this, it does nothing, no? Because it will take the strain, but the stress is going to be 0, and the constitutive tangent is going to be 0. So I think it's going to iterate n times 0, and everything is going to be 0. We're going to try. And then we'll add our version of the elastic law. Okay. This. As you can see, creating code in Python is really faster. Because in here, every time that you modify something to compile, okay. And imagine that now we are working with a class that we have just created. But if you are modifying something in a deep file, like the strategy or the builder and solver, that a lot of files included, each time you modify that, it recompiles a lot of stuff. So in any case, let's run it. As you can see, there's nothing. The ratio, it is constant. So it does not update anything because it's still 0. Everything is 0. It does nothing. Perfect. So let's do what the constitutive law should do.
Tomando estos dos nodos, estos de acá centrales, este y este, no por menos, solamente estos dos nodos. Mira que lo que te dice,
I'm going to declare the strain.
Que da el éxito, para que mando y que son
the values.
540, que es la provincia,
In this case, I'm calling to the strain vector as a reference. So I want, but if I modify the R strain vector, I'm going to modify the container one. But to be sure that I don't modify it, I put the const. The const is this cannot be modified. If I try to, it okay, we have the strain. It should be filled. Now I'm calling to the stress. I will modify it, so I don't put const. And the same with the constitutive. Matrix values constitutive matrix. In here, I'm which are null. I mean the stress and the constitutive tensor are full of zeros. But now what we should do is the stress vector should be equal to C times epsilon. No? I will explain what no alias means. No alias is an optimization operation. Again, if you equal a vector to a something, if you put the no alias, it's faster.
Sí, porque, digamos,
If you don't put it, it works.
que es
But
el
it's
promedio
slower.
del esfuerzo en la
The only case that you cannot use the no alias is when you are equaling no alias something equal to something times whatever. So if the same entity is in the two parts of the equal cannot be used. Okay. Is the problem? Previously we have to compute the constitutive law. But luckily we have a method in the elastic isotropic that does this thing. We're going to call it calculate elastic matrix. Calculate elastic matrix. I'm calling this method as it is mine, but really, in reality, it's a method from the parent class. No?
Sí.
And it takes the constitutive matrix and the R values. Constitutive matrix and the R values. In here, I'm computing the elasticity matrix. No, it will fill the components of the elastic matrix. And now we're gonna do the product of C times epsilon.
Entonces voy a hacer un material aquí, una sola capa con las propiedades de la ficha técnica.
I can do also to be clear.
Como se estaba haciendo ayer, ¿te acuerdas que teníamos el error de
This line is the same of
ponerle a los dos materiales, ¿no?
doing all this stuff.
Y ya con eso, y con eso sí.
What this there is a detail important. This matrix creation, it does not has any size. Well, let's do it like this anyway. Constitutive.
Sí.
You can see here I'm declaring each component of the constitutive matrix. Just to be more clear. Let's see if it compiles, I suppose, because I've copied a lot of stuff.
Dale. Lo otro que te iba a preguntar era como yo estoy libre de clases.
Okay.
Perfecto.
So now it takes the strain. It computes the C. It multiplies C times the strain, and this is the stress. Something is not good. Yeah. Look, I was saying that the stress is the strain. No. Okay. Stress. Did you see my mistake? The autofill sometimes. I was modifying the stress. So no. Now it's fine because it has computed effectively the stress and the constitutive. Now we should obtain. This is exactly the same result that we were obtaining before. Okay. Now we can mess it up. Imagine that we are computing correctly the stress, but the tangent tensor is not correct. Like this. In this case, it is going to iterate more because it is not correctly linearized, but it may converge, okay? But it's going to iterate a lot. Let me put more iterations. Now if it iterates once, it means that the tangent tensor that you have provided, it really complies with the stress that you have obtained. No? If the tangent is not correctly estimated, you can converge, maybe, if it's sufficiently good, but it will iterate more than once, definitely. What we try to do. Only once. Surprising, I mean, it does not really affect. Maybe because we are loading in Z direction. And yeah, maybe it's because of that. So now we're modifying how the constitutive law calculates stuff. But we haven't thought anything about the calculate values to print something or the get values, but it's really easy. I mean, the difficult part is the calculated at this point, in which you have to add the physics to the problem. The rest is bureaucracy that you have to implement in order to see something. It does not really affect this. Curious.
It's Z direction, right? You're loading.
In the Z, yes. But in any case, if I put maybe these components are really big, no? So it really does not really make the difference. But which is the young modulus that they have? I'm gonna put a really low one. Now it should definitely be modified because I'm going to compute the stress according to a really high young modulus, but the stiffness matrix according to a lower young modulus. So it should iterate definitely. One moment. No, it's fine. I don't understand. Calling this method, no? It's not possible. Let's do something. We can use the Kratos Watch utility to see which is the value of something. Okay. For example. Now we should see in our screen the value of the stress and the value of the constitutive matrix to be sure that it is effectively entering to this method, because now I'm quite confused. Yeah, it's entering, so we can see here. So it's entering. The stress vector is a 6 components vector. The stiffness, the tangent tensor is 6 times 6. The weird thing, it is already filled. Why? Not here.
Your young modulus is still a little bit high, no? 30 gigas. I don't know if it's the value you intended to input.
Yeah, but it's definitely lower than this one, no? But
Yeah.
maybe
one tenth of that one, approximately.
should be. I'm gonna. The Kratos watch is not. Okay. It's compiling it. Maybe what is happening is that behind our back, the calculate elastic matrix is, since it's not really modified, it's being computed with the parents method. But yeah, because it really makes no sense that it's always like this. Or maybe we really have to add yeah, I think. But in any case, this is not really important. These are big things. I know what's happening, but I don't want to get into that. The thing is, we have created the constitutive law, more or less understood how it behaves, this parent relationship, okay? Which are the main methods of the constitutive law, how to implement ours, and how to register them, which is the important thing. Then there are more classes in Kratos, no? Because we have the constitutive level, which is our main level in our group, but also we have processes. A process is something that takes the model part and some parameters and computes something. I mean, imagine a process of computing the inertia of a geometry, or a process to duplicate the nodes in the lamination, wherever. This is similar to implementing a constitutive law. It has other methods, mainly execute, but the way that we register the processes is really similar. We have also utilities, which are like a process, but more concrete operations. No? Conditions in which we are not interested because they are already there. I mean, we are not going to implement a point load condition, surface load condition. In here we can see, the custom processes, which is the circuit process, advancing time, whatever. This custom Python folder is to register stuff to be called in Python, because otherwise Python won't know what are you talking about. And the Python scripts, whatever. Okay. Okay, this is more or less what I intended to speak about. I don't know if you Luis, have any doubts or you here.
No, I mean a lot of information, but it was for me at least really interesting. So we have first guideline to start implementing simple stuff in our let's say box of work constitutive laws. I'd like to say thank you very much for spending some time explaining stuff for us. So, of course, there will be doubts and questions,
Yeah.
but bit by bit we can walk through that.
Okay, so let's close this here. In my case, I'm gonna investigate why it's not modifying the whatever. Just for curiosity, I'll tell you.
Actually, I was
Mhm.
curious about one thing you said, that it may be computing this stresses according to the parent class,
Mhm.
but you are not calling this class anywhere, if I'm not wrong.
No, no, I know it, but let me check something because now it's no, no, it's doing it right because if I set the constitutive law to 0, it is effectively using this one. So, oh my God, obviously. No, I know what's happening. I'm stupid. Let me go back, okay? And I'll tell you what's happening. This was how it was implemented, right? So, um, this is the Young modulus, which is taken from the materials JSON. We're computing the constitutive matrix, we're computing the stress, and then we're finished. Obviously, if I modify the constitutive matrix, the stress is going to be modified proportionally, so everything is going to be matching. The thing is, the problem will be if I say the following. For example, the ZZ, after doing the computation of the stress, if I modify this to be Q2 is C2, see, now the stress is not going to match exactly with the linearization, and it should definitely iterate. And if not, I'm going to suicide myself on it.
Okay.
Now, as you can see, it's diverging and diverging and diverging up to not a number. So now everything is, and if we have finished, now we should commit this. And then we push. And when it's pushed, it's in GitHub level, so anyone can see it. I could retrieve it in my PC. You could retrieve it in another PC. You can do the pull request, everything. And last thing, in here we haven't distinguished about this computing stress, computing constitutive matrix, whatever. In general cases, we should have done it. I didn't want to put a lot of stuff just to be clear, no? But in general, there is an if in here, in which we put if constitutive, if compute stress true, then you compute stress, and then if compute constitutive whatever tensor, then you compute it. In order to be more efficient, because sometimes you call the constitutive law only to compute something, so you don't need to build because it is expensive. But I wanted to be really concise in this because it's a lot of information already. Okay, I'm gonna close the recording